Hi, today's talk is on queues in series. This is a follow-up to delay system. In the delay system, we talk about MM1 and multi-server queue MMN and MG1. Okay, now the video for that is also online. So we carry on a little bit forward by looking at, instead of just one queue by itself, you have multiple queues connect in series, connect one after the other. Now, what happened to this? Okay, now what application you have on this is very simple, like when you have packet going through several routers. So in order reach from the sender to the receiver, so you go through several stations, or several router in this case. So in each router, there will be some certain delay. What are the amount of delay altogether along the path? And of course, you can do that for assembly lines and so on. Okay, with that in mind, I'll just go to the slide. Okay, this is the background or motivation. In many situations, a customer requires service from several stations or several queues. Hence, the departure from one queue becomes the arrival to the other queue. So the interarrival time of the second queue is a function of the interarrival time of the first queue plus the service time of the job in the first queue. So with that interrelationship, then we want to find out, is there an easy way to do it? And under what condition, whether that is an easy way to do it, okay? So the example I gave earlier is this path delay over packet internet, for example. So my name is KT Ko or Tim Ko. I've looked at some of the background, the results, and the application. And then I'll just quickly go through the theory behind it, and some concluding remarks, very simple concluding remarks, and some exercise. Now this is the queue in series. So basically, we have this Q1, and that is Q2. So what I'd say was the arrival into Q2 is the departure of Q1. So how do you influence how how does it arrival into Q2? How does lambda 2 in fact is a function of lambda and also the job length. Okay, so there are two single server queue in series. The packet input, the first queue, is assumed to be passed on arrival, so that is an M for this one with rate lambda, and that is a single server queue. So S1, S2 is equal to 1, so that is the 1. So if the server's time are exponentially distributed, so the first queue is MM1. Okay, so if the job are exponentially distributed. So in fact, what we postulate is the second queue is also MM1. Okay, and the results seem to indicate they are independent, and you can easily find joint probability given you know each condition of each Q1 and Q2. So this is the result. Basically, we just say the joint probability is equal to the probability of independence. So you have the first Q of I, probability I multiplied second Q of J, as they are both separate Qs. Okay, so this is the result. And more than that, if there are two queues in, if there are MM1 queue, so the MM1 result holds. Okay, when can it hold is very simple. When row 1, lambda 1 are less than 1, and they are row 2 is also less than 1. Okay, so with that conditions, that row 1, row 2 are less than 1, and the joint probability Pij equal to 2 probability in product form, as they are independent from each other, and you can use the MM1Q result to get the joint probability. Okay, so with that, I'll just give you an example of how it works. So example, we have two single server queue connect in series. Customers are in Q1 and the Poisson process arrival, and lambda is equal to 15 per second, and mu 1 is equal to 20, and mu 2 equal to 18 per second. 18 arrival, 18 departure, lambda is 15 arrival per second. Now, if you want to know what is the arrival rate of first Q lambda 1, of course, that is the 15 per second. In fact, for the second Q, lambda 2 is also 15 per second. Why? Because mu 1, which is 820, is larger than lambda, and mu 2 is also larger than lambda. Okay? So in fact, we have the output rate from Q1 equal to the output rate from Q2, which is equal to the external arrival rate of 15 per second. Okay, because mu1 is larger than lambda, mu2 is also larger than lambda. And if you want to know this total system delay, is just the total system delay of Q1 and Q2, and okay, and that is if you know the MM1 result, and that is the total system delay for one single MM1Q, and that is the second MM1Q. And because mu1 is 20 minus 15, so it's 1 over 5, and mu2 is 18 minus 15, 1 over 3. So that's why you have 0.55. Okay. All right, with that, we just move forward a little bit. Okay, so the theory behind it is quite simple. We are not doing a proof, we are doing a demonstration why it could be a product form solution, okay? The assumption is the interarrival time of Q2 are independent of the service, are independent of service time in Q1. And if that is the case, then we can show that the product form solution is true, okay? So let's the joint probability I is the per customer in Q1 and J is a customer in Q2. Okay, so and with that, and let's assume there are different departure rate for each different state for each customers, but we relax that later on. Okay, so service rate in Q1 they're I customers, service rate in Q2 when they are J customers. So with that notation, we just move forward a little bit. So this is a two-stage transition diagram, and one is for I is for Q1, J is for Q2. Now, as I said, we relax the state dependence departure rate. Okay, so basically we just have this. They are all mu1 or mu2 constant. They are not state depending on the state. Okay. So basically you will see the leaving of ij and the arriving into ij, those sums, those should be equal for statistical equilibrium. Okay, so what is the leaving part? Leaving part, okay, and there are entering part. Okay, now what are we looking at? We're looking at two queues in series. And this is mu1. This is a second queue. And that is mu2. And that is the external arrival. And this is Q1. This is Q2. Okay, that is I, the number of jobs in the system, and J, that's J. Okay, so basically we have this arrival. When is leaving IJ? Leaving IJ is this. When there's outside, when, oh, that's something wrong. Okay. So we have this. So we have this, the leaving part and the entering of IJ. So let's look at the leaving IJ. So one of this is this one, leaving IJ. That's one part. What's that happen? If you are IJ, then and that is external arrival, so I become I plus 1. And which is the other one? Is this one. And I minus 1 in Q1, J plus 1 in Q2. And when that happens, then you have a departure. So when you're in IJ, there's a departure from the first Q. Then you have one more in the second Q. Okay, that's leaving. And leaving is this one. And which other one is leaving IJ? Is this one here. Okay, so you have IJ stage, and then you have a departure from the second Q. So that becomes J minus 1. What about entering IJ? So if I put the symbol entering IJ, this is one of them. A departure from second Q from J plus 1, that will become J. And departure from the first Q when the state AI plus 1, J minus 1. So this departure join here and become IJ. All right. So, and that is, what's about the third one? Is an external arrival, and that is from I minus 1 become I. So there are 3 states, which is for entering, 3 states for leaving, and those 2 should be equal for statistical equilibrium. So with that, so let's look at, so this is the leaving, probable leaving IJ is equal to probable arriving IJ. So you put all the equation together, and then they 2 are equated, okay? So if we assume we try a product form solution to separate those 2. So Pij become P1, P2, and do the same for this, this, and this, okay? So just separate those 2 as their product form solution. And then the other thing we do is assume MM1 solution. So you assume you substitute the value of P1 using this term, because that is MM1 result. So just simply rho 1 and rho 1 to the power I, where rho 1 is lambda 1, mu 1. Okay. So with that, and then you substitute that result into here, and here. So if you do that, then what you have is and cancellation, and then you will have this result left over. Now, basically, this result is an MM1 system on Q2. Okay, so basically, you just say simply is the arrival in the second Q is also lambda, which we have shown that is correct if mu1 and mu2 is larger than lambda. Okay, and the solution for second Q is this. So we have shown the product form solution is one possibility. Okay, it's not a proof, it's just a demonstration. So the conclusion for this is if you have a product, if you have two Qs in series, two MM1 Qs in series, they are independent of each other. If mu1 is larger than external arrival, mu2 is larger than external arrival. And then they are product form, the joint probabilities are the independence of each, a product form of each Q. So the MM1Q result can be used for each individual Q, okay? So with that, we go to the final exercise, which I propose for you. So in this case, you have the lambda equal to 10 customer per minute, okay? And the mu1 is 20 customer per minute, 15, and I just asked you for some detail, the state transition, the system diagrams, and the expression Pij in terms for Q1 and Q2, and then find the numerical solution for this, and ask you to look at what assumption you use, and the queuing delay you can calculate for. Okay, thank you very much for your time, and this is the end of this talk.